Good morning, everyone. My name is Malik and today I'll be discussing fiber optic technology. Can anyone tell me the definition of optical fiber? Well, in fiber optics, the optical fiber is a flexible, transparent fiber made by drawing glass, which is a silica or plastic, to a diameter slightly thicker than that of a human hair. And optical fibers are used most often as a means to transmit light between the two ends of a fiber and find wide usage in fiber optic communications, where they permit transmission over long distances at higher bandwidths than wire cables. Fibers are used instead of metal wires because signals travel along them with lesser amounts of loss. In addition, fibers are also immune to electromagnetic interference, and a problem with metal fibers also wires suffer from excessively. Fibers are also used for illumination and are wrapped in bundles so that they may be used to carry images, thus allowing viewing in confined spaces, as in the case of a fiberscope. Now, if you look closely at a single optical fiber, it's made out of three main things, which is the core, the cladding, and the buffer coating. The core itself is a thin glass center of fiber where the light travels. The cladding is the outer optical material surrounding the core that reflects the light back into the core. And the buffer coating is plastic coating that protects the fiber from the damage and the moisture. It's mainly used with hundreds or thousands of these optical fibers, or arranged in bundles and optical cables, and the bundles are protected by the cable's outer covering called a jacket. And then we have, starting out in the history, we have these two, Daniel Colliding and Jacques Babinet, and they pretty much first demonstrated the idea to make fiber optics possible, which was in Paris in the early 1840s. Also, John Tyndall included a demonstration of it in his public lectures in London around 12 years after that. Now, the image transmission through tubes was demonstrated independently by the radio experimenter Clarence Hansel and the television pioneer John Barrett in the 1920s. This is Clarence Hansel on this side. This is John Barrett over there. And also, the principle was first used for internal medical examination by Heinrich Lamb in the following decade. Now, the first fiber optic semi-flexible gastroscope was patented by Basil Hershowitz, also C. Peters and Lawrence Curtis, which were researchers at the University of Michigan in 1956. And in the process of developing the gastroscope, Curtis produced the first glass-clad fibers, and previously optical fibers had relied on air and impractical oils and waxes at the low-index cladding material. The first working fiber transmission system was demonstrated by German physicist Manfred Borner in the research lab in Ulm in 1965, which was followed by the first patent application for this technology in 1966. Charles K. Cowell and George Hockham of the British company Standard Telephones and Cables were the first to promote the idea that the attenuation in optical fibers could be reduced below 20 decibels per kilometer, making fibers a practical communication medium. And they proposed that the attenuation in fibers available at the time was caused by impurities that could be removed rather than by fundamental physical effects such as scattering. They correctly and systematically theorized the light loss properties for optical fiber and pointed out the right material to use for such fibers, silica glass, and they also won a Nobel Peace Prize in Physics in 2009. And some of the advantages that optical fiber wire has over copper wiring is a broad bandwidth, immunity to electrical interference, low attenuation loss over long distances, electrical insulator, and material costs and theft prevention, also security of information passed down the cable. And some of the many uses of the optical fiber include communication, sensors, also power transmission as well. And there's optical fibers come in two parts. There's a single mode fiber, and you also have the multi-mode fiber. Now with the single mode fiber, a significant fraction of energy in the bound mode travels in the cladding as in the evanescent wave. And the most common type of single mode fiber has a core diameter of 8 to 10 micrometers and is designed for use in the near infrared. The mode structure depends on the wavelength of the light used, so that fiber actually supports a small number of additional modes at visible wavelengths. And then you also have the multi-mode optical fiber. And it has a larger core diameter, which is greater than 10 micrometers, and it may be analyzed by the geometrical optics. Such fiber is the multi-mode fiber step index, and the rays of light are guided along the fiber core by total internal reflection. And I have a video on how it's made.
Or go on the internet. What you say or type travels to its destination through fiber optics. Voice and data gets transmitted via pulses of light through hair-thin glass fibers. Those fibers start out as large glass tubes. First, workers unwrap the tubes. Then they submerge them in a corrosive bath of hydrofluoric acid that removes any oil residues. Then they set a tube into each end of a layer. As the tubes spin, they're heated with a hydrogen-oxygen flame. When the glass turns white, it's getting close to hitting peak temperature. At about 3,500 degrees, the two tubes fuse together. They put this new longer tube onto another lathe. As the tube spins, they inject a mixture of chemical gases inside, while a traversing burner heats everything up. The gas mixture contains liquid forms of silicon, an abundant chemical element found in nature, and germanium, a chemical element similar to tin that's used as a semiconductor in transistors and other electronic devices. As the gases heat, they undergo a chemical reaction that leaves a white soot on the inside of the glass tube. The heat fuses the soot, forming what will eventually become the core of the optical fiber. The glass tube itself will form the fiber's covering. When there's enough fused soot, they turn up the heat until the soot itself turns into glass. Then they heat the glass tube enough to soften it, and to soften the new glass inside. The intense heat eventually makes the tube collapse on itself to form a solid rod. The internal structure of the optical fiber has been achieved. But it's in the form of a big bulky rod called a preform, so the next step is to thin it out. First, they excise the preform from the uncollapsed section of the glass tube. Then they install it vertically into the drawing tower, which will draw out the final shape. The drawing tower's oven heats one end of the preform to 3,600 degrees. Gravity helps pull it down, like honey dripping from a spoon. Then, using a glob of glass as a weight, they stretch the soft glass and keep stretching it until they've formed a thin glass fibering. A series of pulleys measure the tension on the fiber as it's being drawn. A special monitor makes sure the fiber is precisely the right diameter, just 5/1000ths of an inch. Then the fiber passes through UV lamps that bake on an acrylic coating to protect against dust and other contaminants. Finally, the fiber is rolled onto a drum. From here, it's either shipped out as is or put into a cable. Fiber optic cables are expensive to produce, but they're smaller and lighter than traditional copper cables. They carry more information and need fewer repeaters to keep the signal from deteriorating. And unlike copper cables, they're immune to electromagnetic interference. They're also hard to tap without being detected. And all this is made possible by a complicated process based on a very simple principle: light traveling through glass.
So there is pretty much an example of the process of making the optical fiber. And the standard optical fibers are made by first constructing a large diameter, also known as the preform, with a carefully controlled refractive index profile, and then pulling the preform to form the long, thin optical fiber. The preform is commonly made by 3 chemical vapor deposition methods: inside vapor, outside vapor, and vapor axial deposition. And then the optical fibers are connected to terminal equipment by optical fiber connectors. And here we have the connectors, which are usually the standard types, such as the FC, SC, ST, LC, MTRJ, and SMA, which is designated for higher power transmissions. All of these standardized connectors are physical contact type, where the mating surfaces touch each other to achieve the lowest possible attenuation, and all but the ST have a keyed ferrule that allows an angled mating surface to reduce reflections that can cause problems with laser transmitters. And optical fibers may be connected to each other by connectors or by splicing. That is joining 2 fibers together to form a continuous optical waveguide. The generally accepted splicing method is arc fusion splicing, which melts the fiber ends together with an electric arc. And I have a quick video of the termination of the splicing process. right, so for those of you all who aren't in the cabling class, if you hear all that noise in the lecture room, that's what we're doing, the termination process. And we also have the splicing process as well.
Coaxial cables. If you have a cable that needs to be joined together, like this, let's say, all you have to do is cut the cable with special cable strippers. You could use a knife if you knew exactly what dimensions the cable had to be spliced and at what depths, but that stripper makes things a lot easier. Basically, it turns the cable into something like that. Just make sure there's no outer braid touching the center conductor. And then you have the compression cables or compression plugs that you put onto the cable. Make sure the dielectric comes to the seats at the bottom of the F plug on both. And these compression cables need to be crimped. That's what this tool does. It crimps them down tight. You can't remove these at all, plus these are weatherproof. They can be left out in any kind of weather. And then what you have to get is a barrel connector like this here. This barrel connector goes on to each one. It screws in like that on one side, and then the other side I can put this plug in. And that screws into that side of the barrel connector. And that's a completely weatherproof connection with no chance of coming apart. And that's your how to splice a cable.
So this is a box.
Press.
All right, does anyone have any questions? Okay, that's the end of my presentation.